In this session, I will discuss about the discrete probability distributions. According to the variable, according to the nature of the variable and the situation of applying the probability concepts, it is important to have an idea regarding the underlying probability distribution. In the previous sessions also, you have got a very brief idea regarding about the probability distribution. When we are discussing these concepts, we have discussed these concepts as the early stages of this session. Therefore, at that time also, we have discussed about according to the nature of the variabilities, because we know that we are having discrete type of variables and continuous type of variables. We are having the discrete variables, as well as we can see that we have to deal with the continuous type variables as well. Therefore, according to the nature of the variable that we are using, the underlying probability concepts, when we are applying underlying probability concepts, then we have to pay our attention regarding the discrete probability distribution as well as the continuous probability distribution. Therefore, this concept is now directly applied with the previous session that we have discussed about this discrete and continuous case inside the probability distribution. But in this section, we will only discuss about the discrete probability distribution. Therefore, we can simply say that if there is a probability distribution associated with a discrete random variable, is that if the considered random variable is a discrete random variable, then the associated probability distribution with this discrete random variable is said to be a discrete probability distribution. Therefore, now we'll look about several types of the discrete probability distribution. In this session, I will discuss about several types of discrete probability distribution, but apart from these distribution, there are many more discrete probability distribution in statistics. But here, I will just select a few of them and I will discuss them one by one in this session. Okay. Prior to move for the probability distribution, first we will have an idea regarding the Bernoulli random variable. Rather than saying this as a probability distribution, this can be simply say as a random variable, and nature of the random variable is said to be the Bernoulli. That is why we can say this as the Bernoulli random variable. If you are considering a single trial, suppose that you are performing an experiment, and for a single trial of that experiment, you are getting a random variable which is having only two possible outcomes. It means that if it to be a Bernoulli random variable, to be a Bernoulli random variable, I am abbreviating it as RV. To be a Bernoulli random variable, there are two conditions. It means that we are considering a single trial. We are considering a single trial, and in this single trial, you should observe only two possible outcomes. You may get one of these two possible outcomes. Two possible outcomes. It is simply if you are considering these two possible outcomes, and we are saying that these two possible outcomes are mutually disjoint or the mutually exclusive. It means that occurrence of one outcome prevents the occurrence of the next outcome. Therefore, that is why we can say that these are mutually exclusive outcomes of the occurrences. And when we are discussing about this Bernoulli random variable, we are naming these outcomes as success and failure. Here I have mentioned that there are two possible outcomes, and among them one would be success outcome and the next would be the outcome saying as the failure outcome. Therefore, there will be two situations. One is associated with success and next one is associated with failure. Therefore, if you are having a random variable which satisfy all these conditions, it means that we are considering a single trial, and in this single trial we can have two possible outcomes which are mutually exclusive, and then we can name them as success and failures. Then such a random variable is said to be a Bernoulli random variable. If we are considering a random variable, we should be able to define a sample space for any given random variable. If you are considering the Bernoulli random variable, we can define the sample space for the Bernoulli random variable as success and failure. Success and failure. It is because these are the two possible outcomes that we can see inside the Bernoulli random variable. That is why we can define the sample space for the Bernoulli random variable as success and failure. And sometimes apart from the success and failure, we tend to use the success as 1 and failure as 0, or vice versa. It means that you can name success as 0 and failure as 1. Anyhow, these are just the notations only. Apart from that, we are not going to worry about these numeric values much more. Anyhow, we are paying attention towards these notations as ones and zeros. And most of the time, we are, if it is a Bernoulli random variable for a Bernoulli experiment, we are saying this as random variable. If you are performing this experiment for a single trial or only for one time, then we can say this as a Bernoulli experiment. Therefore, generally we are looking forward for the event of the success if we are performing this Bernoulli experiment. And based on this event of success, we can model this Bernoulli random variable. Therefore, if we are modeling this Bernoulli random variable, we can write down this Bernoulli random variable in this way. Suppose that x is a Bernoulli random variable. We can let x is the random variable we are considering, and we can say that this x follows a Bernoulli random variable. Here we are writing down it is the lowercase letter p. Generally, this p said to be the probability of success. Here we says that p is the probability of the success event. This is what we are saying here. This is the lowercase letter p, and this p is used in here. Therefore, we are using this the notation tilde to denote it follows a distribution. And here we are saying the random variable, and this is the type of distribution we are having, and the parameters used in the distribution is mentioned here. And now you can see that x can have in two possible outcomes. One is failure and next one is the success. Here it is mentioned that x and the probability of x equals x. Probability of this capital X equals the lowercase letter x. Here these are the lowercase letter x values. We can say this as the success, if it is success. Then we can name this as 1, or else we can name this as 0 as failure. I have just interchanged these two rows. First and second row has interchange here. It is because for the easiness of the explaining the concept. Here I have previously told that we are most of the time we are pay much more attention towards the event of success when we are modeling this Bernoulli random variable. And suppose that the successive probability of this experiment is given as simple p. Suppose that if it is given as simple p, then the failure event can be considered as 1 minus p. It is because we know that there are only two possible outcomes. In the sense, it means that these are exhaustive events as well as mutually disjoint events. Therefore, by combining all these theories, we can say that if the success probability is given as p, the failure probability will be equals to 1 minus p. Okay, now we will focus on an example regarding this Bernoulli random variable. Suppose that you are conducting an experiment of tossing an unbalanced coin. It is stated as unbalanced coin having the chance of getting head is 0.7. Therefore, according to this experiment, what we know is if we are tossing this coin, the probability of getting a head is equal to 0.7. Since this is an unbalanced coin, this value is differ from 0.5. And if it is given as consider the event of obtaining head as a success event, it is given that successive event is obtaining head. Therefore, this can be considered as the successive probability. It is because the success event is given as obtaining a head. But if it is given as a successive event as obtaining a tail, then what we have to consider as the successive probability as 0.3. It is because obtaining tail would be the successive event at that time. But in this example, it is given as event of obtaining head as the successive event. Therefore, we can say this value is equal to P. Therefore, we can say that probability, since probability event of obtaining head is the successive event, we can consider that value of P is equal to 0.7. And if you identify the suitable probability distribution, the question is asked as that identify the suitable probability distribution. Here, if you are considering a single trial, we'll consider it as a single trial, consider an experiment of tossing. It does not say us that how many times are they repeating, or there is no sense of repeating this experiment. Therefore, we can simply consider that they have tossed this coin for only one time. Therefore, if you focus on this experiment, how we can model this, we can say that the solution is given here. Suppose that the obtaining head is the success event, then obtaining tail would be the failure event. First, we have identified what is the successive event and what is the failure event. And according to this example given, and the if we are performing this experiment, we can see that head and tail both cannot be occur at the same time. It means that the occurrence of one event prevents the occurrence of the next event. It means that head and tail cannot be obtained at the same time. Therefore, we can consider that these two are mutually exclusive events. These two are mutually exclusive events, and then collective exhaustive event. It means that there cannot be any other events apart from the obtaining head and obtaining tail. Therefore, we can consider these are the only possible outcomes. Therefore, we can see that we have considered a single trial, and obtaining head and obtaining tail are the only possible outcomes. Therefore, we can see that two possible outcomes as well as those are mutually exclusive event. Therefore, according to this problem, it is given that consider the obtaining head as the successive event. If we are modeling this, or if we are trying to identify the suitable probability distribution for this event, this can be simply modeled using the Bernoulli probability distribution, or just the Bernoulli random variable. Therefore, if we are considering X as the event of obtaining head, let X is the event of obtaining head. And therefore, we can say that we have fulfilled all the conditions which need to be a Bernoulli random variable. Single trial is there, two possible outcomes, mutual exclusive. And we have identified that those are exhaustive events as well. Therefore, X can be modeled using a Bernoulli random variable. Then the successive probability can be considered as the 0.7. Therefore, we can say that X follows a Bernoulli distribution, or X is a Bernoulli random variable having the successive probability as 0.7. Therefore, we can construct the probability distribution in this way. Here we are letting the letter X, and here we are saying this X equals lowercase letter x. Here we can say this is X equals the head and X equals tail. then we know that probability of obtaining head is 0.7. Therefore, probability of obtaining tail is 0.3. Therefore, this is what we can say as the solution. Final solution for this problem is, we can say that x follows, or x can be modeled using a Bernoulli random variable, and the probability distribution of x can be tabulated in this form. Here you can see, here in the other way around, it is I have changed these two values. First, I have taken the failure, and thereafter I have mentioned the success. Apart from this head and tail, if you wish, you can say head as your number 1, it is the success, and tail as 0, it is failure. But if you are using this 0 and 1, definitely you have to say that 1 denotes the obtaining head and 0 denotes the obtaining tail. Therefore, it would be better if you can write these notations as well. Now we will move for the first probability distribution. Here we will discuss about the binomial distribution. Binomial distribution is said to be a discrete probability distribution. This is what can we say as a discrete probability distribution. It is because based on the discrete random variable, this binomial probability distribution is made up of. Therefore, when we are considering this binomial distribution, rather than saying this as made up from discrete random variable, it is better to say this as this is actually a collection of Bernoulli random variables. It is quite as using rather than saying as binomial, this should be Bernoulli. Therefore, the collection of Bernoulli. Okay, in the next line, it is actually mentioned a collection of identical and independent Bernoulli trials. This is Bernoulli distribution is for this binomial distribution is for binomial random variable, and this binomial random variable is formed up using a collection of Bernoulli trials. When we are considering about this Bernoulli trials, there are two other conditions. Those should be identical and independent. Identical and independent Bernoulli trials should be there, and the collection of these Bernoulli trials formulate a binomial random variable. Therefore, this binomial random variable, this counts the number of successes in many independent identical Bernoulli trials. Here we are considering, here it is actually a counting technique we are using here. Suppose that simply if I explain this, suppose that you have repeated an experiment for several number of times, and among that number of time you are identifying how many successes were there. It is the simplest idea behind this binomial distribution. What we have done at the Bernoulli random variable was we have run an experiment for a single trial, and we have just observed whether it is success or failure. Now we are repeating the same thing for large number of times, or the several number of times, and among that we are identifying how many successes are there. That is why we can say this as a collection of Bernoulli trials. If you are considering a single run of an experiment, it can be actually considered as a Bernoulli trial, and these trials should be independent and identical. And for any uncertain situation or an experiment that is marked by the following properties can be modeled using a binomial distribution. Simply, if I explain this, if you need to model, if you need to fit a binomial distribution, then following conditions should be satisfied. There are 4 conditions. Here we are saying that fixed number of trials. First condition is fixed number of trials. It is because when we are going to performing a binomial experiment, first we need to fix number of trials. In simply, these things are just stated in the explained in the this paragraph. But apart from that, if I explain it here, suppose that you are going to conduct an experiment. First, you need to fix how many times that you are repeating this experiment. Suppose that you are tossing a coin. First, you have to fix. Okay, I am tossing this coin for 10 times. Or I am tossing this coin for 50 times. Therefore, first you need to have fixed number of trials. Number of trials cannot be vary if it needs to model using a binomial distribution, or else if you are going to perform an binomial experiment. This is the first condition that should be satisfied. It should be fixed number of trials. And the next thing should be trials should be independent. It means that trials should not be dependent. Those should be independent. It is because if you are tossing, if I take the experiment of tossing a coin, if you are tossing a coin for this time, it should not be affected by the tossing of the previous one or the latter tossing. Therefore, the trials should be always independent. It is here also, it is given that independent Bernoulli trials should be included here. Therefore, first condition is fixed number of trials. Second condition is trials should be independent. And the success probability, the third condition is success probability should be a constant throughout each trial. It means that it should be identical. It is because the probability cannot be vary from one toss to the next tossing. If the probability is varying, then we cannot use this binomial distributions to model this type of experiment. Therefore, if we are performing an experiment or binomial experiment, then the successive probability should be always a constant throughout that experiment. It means that if we are running these Bernoulli trials for several number of times, those should be identical. And each trial should have only two possible outcomes. Even though all these three conditions are satisfied, if you are having more or less than these two possible outcomes condition, then you cannot model this using binomial distribution. Therefore, each trial should have only two possible outcomes. Here, previously also we have said that those should be successes and failures. Therefore, these are the four conditions which should be satisfied if you need to model a variable using a binomial distribution. Here some examples are given here. It says that binomial distribution is a distribution of counts. It is because we are repeating an experiment for several number of times, and among this number of time we are just counting how many successes were there. That is what we are observing. Therefore, we can say we are just having the counting only. That is why we can say that binomial distribution is a distribution of count. And this always counts the number of successes, and according to the situation, we have to define the event correctly if you are using this binomial distribution. Therefore, generally counts the number of successes in a certain number of trials. Thus, the binomial distribution gives the probability of exactly X successes in N successive trials. Suppose that if you are repeating your experiment for N number of times, and you have observed that out of this N number of times, X were the number of successes you have observed. Therefore, this binomial distribution gives us the probability of exactly X successes obtained out of N number of trials. It is simply as if you are tossing a coin for 10 times, then if you need to observe what is the probability of getting exactly 7 heads, then you can model it using this binomial distribution. Here some examples have mentioned here, tossing a coin for 10 times and observing number of heads obtained. Another example, obtaining number of defective items from a lot of 200 items, then number of male birds out of next 30 birds can be considered as some examples for this binomial distribution, or the events which can be modeled using the binomial distribution. Now we will have a look about the notations which are used inside this binomial distribution. Suppose that x is the variable that you are considering, and suppose that x follows a binomial, x is a binomial variable. To be a binomial variable, it should satisfy all these four conditions. Therefore, we can say if it is a binomial variable, we can model it using a binomial distribution. Therefore, we are saying that x follows a binomial distribution. To denote it, we are using these letters bin. It is to denote the binomial distribution, and here we are having two parameters. N is the number of trials and P is the successive probability. Here this says that x follows a binomial distribution, and this has n number of trials and P is the successive probability. Here these things are mentioned. X is the event of success, P is the successive probability, and N is supposed to be the number of times or number of times repeated, or we can simply say that N is the number of trials. And this each trial is a Bernoulli trial, and the collection of Bernoulli trial sets the binomial variable. Therefore, we can say this this can be denoted as x follows a binomial distribution having n number of trials and p successive probability. If it is a distribution, then this can have a distribution function as well. Therefore, the distribution function for binomial distribution can be written as, here we are counting the probability of the random variable x having a particular value stated as simple x. This can be obtained as, here we are saying, using these combinations and permutation notation. This is NCX. Here we will say this as NCX. It means x items chosen out of this n number of trials. Then this times p to the power x, where p is the successive probability, and then here it uses 1 minus p, and this equals to n minus x. Some are referred this 1 minus p as, sometimes 1 minus p is said to be given as q. If you see q in any note or internet, then just replace it as 1 minus p. Actually, the q is the failure probability. In other words, we can say it as 1 minus p. And the notation NCX stands for, it is given as n factorial times n minus x factorial divided by x factorial, where n factorial is supposed to be multiplication from 1 to n. It is n minus 1 into n minus 2. Likewise, we have to have the multiplication. Then likewise, we are having 3 times 2 times 1. Likewise, up to 1, we are considering the multiplication of the numbers. Therefore, if you are familiar with this equation, you can directly type it in calculator and obtain the value, or else you can use, if you are using a scientific calculator, you can simply use this NCX. You can obtain the value for NCX using the calculator. And if I say about these terms, here n is supposed to be the number of trials. N is supposed to be the number of trials, and P is supposed to be successive probability. And X is supposed to be number of successes. Number of successes obtained, and this uppercase letter X is the said to be the successive event. This is actually what you have to be familiar with this quantity, and this is actually somewhat additional part that you have to need if you are performing this calculation, and here the explanation of each term is mentioned below. And now we will just have a look about the characteristics of the binomial distribution. And here I have mentioned several characteristics of binomial distribution. We'll go them one by one. The probability distribution, or we are saying the probability mass function, in the previous sessions, we have in detail discussed about this probability mass function and so-called theories. Now, therefore, in generally, we are defining the this probability mass function using the lowercase letter. Therefore, this is supposed to be simple fx, and this stands for the probability that our random variable x having the value this lowercase x here, lowercase x is only supposed to be a the value which is taken as the number of successes, and this is actually what we have written here, and this is equal to ncx times p to the power x times 1 minus p to the power n minus x. Here this is what we are saying as the probability distribution function or the probability mass function. And cumulative density function can be obtained. It can be considered as, since this is a discrete probability distribution, using the summation we can obtain. Here this is that fx. Here this fx is supposed to be probability that uppercase letter less than or equal to a particular value of x, and this can be obtained using summation, where x goes from 0 to n, 0 to x, particular value of x. Then this is ncx times p to the power x 1 minus p to the power n minus x. Here this is how we are denoting the cumulative density function for a binomial distribution. And the expected value of the binomial distribution can be obtained using the same concept that we have used previously. Expected value for a discrete probability distribution was used as summation of x times px. So x times px, and here we can say that it is x times, here it is px equals x. And instead of this quantity, you can substitute this ncx p to the power x times 1 minus p to the power n minus x. And for all x, we are saying these values. Therefore, if you are performing this calculation, and it will be somewhat a lengthy proof, but I'm not going to show it here. Therefore, the calculation gives us a value for the expected value of the variable x as n times p, where n is the number of trials and p is the successive probability. Therefore, if you are having a binomial distribution for this binomial random variable x, the expected value of x can be obtained as n times p. And the fourth characteristic that we are going to consider under binomial distribution is the variance of the binomial distribution. Using the same concept, what we have used previously was ex squared minus ex to the power 2. Using this concept, you can obtain the variance of the random variable. Therefore, by solving this, or else you can use this concept as well. It is x minus mu to the power 2 times this the summation for all x, x minus mu to the power p times, or the px. Therefore, this leads us to the variance of the binomial distribution. This leads the calculation as n times p times 1 minus p. Sometimes you can see this as n times p times q. Q has written instead of 1 minus p. Therefore, these are the important things actually we have to we have to keep in our mind as the characteristic of the binomial distribution. Probability mass function, and then here we are saying the cumulative density function is this probability mass function, then expected value, or simply we are saying as the mean value, and here we are saying the variance of the distribution. It is obtained as n times p times 1 minus p. Apart from these characteristics of the binomial distribution, there are two more characteristics which are generally using. Therefore, if I go through those two as well, if you are considering, even though these are discrete and continuous, we can have some approximations. If you are having a binomial distribution, this binomial can be distribution can be approximated by the normal distribution. Therefore, if you are having a binomial distribution having the large n, it means that if you are having large number of trials and P or Q are too closer to 0, it means that P or Q which are too close to 0, then this neither P nor Q close to 0, it means that these are not closer to zeros. It is quite around 0.5 or something, a value like that. Therefore, if you are not having the values which are closer to 0, it is quite like this that why I now you may have just a curiosity that why I say that P it is nearly about 0.5. It is because suppose that if P is equal to 0.999, then Q will become, or Q which is equal to 1 minus P, this will become 0.001. It means that becoming of one value which is very larger makes the other value which is very closer to 0. But if you need to have this normal approximation, neither P nor Q are too closer to 0. Therefore, in these situations, you cannot just model using this normal approximation. But if you suppose that P is very closer to 0, suppose that we are having P is equal to 0.5001, then you may have the 1 minus P, or simply we can say it as Q. This would be equal to 0.4999. Therefore, this neither P nor Q are closer to 0. Therefore, in such situations, with having large number of n's, we can approximate the binomial distribution to a normal distribution. Therefore, actually, this normal distribution is a continuous probability distribution. Here I am just stating about that we can approximate binomial to a normal distribution, and if you are approximating, then these are the values we are obtaining from the binomial distribution. The value of n is obtained using binomial distribution, and value of P is obtained using binomial distribution, and this conversion makes the binomial distribution into a normal distribution. That is why we are saying that the binomial distribution can be approximate using a normal to a normal distribution. Therefore, the concept behind this approximation is n should be a large value. N should be a large value, and neither P nor Q closer to 0. No Q closer to 0. Therefore, most of the time, if you are having the values which are closer to 0.5, it is because the very large value of P, the maximum we can take for P is 1. In such situation, Q becomes 0. Therefore, the becoming one value which is very large or closer to 1 makes the other value closer to 0. Therefore, we can have a value which is having a moderate value like as 0.5. If one value is 0.4, next would be 0.6. Therefore, none of these values are closer to 0. Therefore, in such situations, we can apply this approximation of the normal approximation of binomial distribution. And there is another approximation technique we are considering. It is the Poisson approximation of binomial distribution. Here we are considering that if we are having a large number of ends, suppose that n is a very large number and p is supposed to be a very small number. It is infinitely small. It means that p is a value which is very closer to zero. It means that the successive probability is a very low value. Suppose that if you are having n is equal to 1000 and suppose that p is a very smaller value 0.001, then we can approximate our binomial distribution by the Poisson distribution. And in the latter part of these discrete probability distributions, I will discuss about the Poisson distribution. Then this can be modeled using Poisson distribution as one parameter, say as lambda. Then this can say that lambda equals n times p, where n is coming from n and p are coming from the binomial distribution, where n is the number of trials and p is the successive probability. Therefore, these two approximations can be used for a binomial distribution. The first one is used if n is large and neither p nor q are closer to zero. Then in such situation, we can approximate it to a normal distribution. In the next situation, we are having n is a large value, but p is a very small value, which is very closer to zero. In this situation, we can approximate our normal distribution by Poisson distribution. Here, I would like to say that this normal distribution is a continuous probability distribution, but the Poisson distribution is still a discrete probability distribution. Here it is mentioned that this n goes to infinity. It says that n is a large value and p goes to zero, that p is a value which is closer to zero or very small value. Here some examples are included for binomial distribution. But anyhow, I will take one of them for explaining how we can apply this binomial, the concepts that we have discussed so far of the calculations. Therefore, if I take the first example says that assume that probability of obtaining head by tossing an unbalanced coin is 0.7. Here it is given that probability of obtaining head is 0.7. Most probably this should be an unbalanced coin. And since we are considering the event, here we will consider according to the given problem, we have to identify the event. Here, if I go through all these problems, they all are just interested in obtaining heads. Therefore, I will let x is the obtaining an head. Event of obtaining an head. On the tossing of the coin. Therefore, here also the probability of obtaining head is given. Therefore, what we can simply use is we can say that obtaining head. Suppose that prior to this part, if I explain this matter, if you are tossing a coin, you may get either head or tail. Here, if you are suppose that the coin has tossed for 5 times, it means that fixed number of trials. Therefore, simply we can have this as using, we can model this using binomial distribution, and we'll assume that all the trials are identical and those are independent trials. But generally, these things are given, but if it is not given, by assuming that we can follow this, we can use the binomial distribution here. If you need to use the binomial distribution, then we need to have the value for n and we need to know the value for p. We know that it says that the coin has tossed for 5 times. Therefore, we can say that n equals 5 and the successive probability p is given as 0.7. Now, in the first part, it asks the probability distribution of number of heads obtained. First, we are asked to find out the probability distribution. Therefore, prior to find out the probability distribution, I can say that using the notation, I am saying that X follows a binomial distribution having 5 priors and successive probability as 0.7. Therefore, X is the number of heads obtaining a head, and num X rather than saying this is the event, but here what we are observing is X is this should be lowercase letter x. Here the lowercase letter x is number of heads obtained, and n has given as 5, p is given as 0.7. Now what at the very first part of this question asks us the find out the probability distribution for number of heads obtained. Therefore, first we'll need to identify what are the possible values that we can take for x. It means that the possible values of x, or possible values that we can consider as number of heads obtained. Here it is given that I have identified that suppose that you are tossing a coin for 5 times. Therefore, the maximum you can identify is 5. Then you can observe 4 heads. Then 3 heads will be there. 2 heads can be there. 1 head can be there, and no heads. It means that 0 heads. Therefore, we can set x is going from 0 to 5, and what we know is these are the possible values of x. And prior to this, if I write down the probability distribution function of x, if I write down it using the fx, then this can be considered as ncx times p to the power x times 1 minus p to the power n minus x. Here, but what we know is we know the value of n and we know the value of p. Then what we can write is n is equal to 5. Then we can say this as 5cx. We know that the probability of p, or the value of p, is 0.7. Then 1 minus 0.7, n is 5 minus x. And if you solve this furthermore, then we can say that fx equals to 5cx 0.7 to the power x, 1 minus 0.7, it is 0.3 to the power 5 minus 6. Therefore, this is what we can now write down as the probability density distribution function, or the probability mass function. Now what we need to do here is we have identified that possible values of x are 0, 1, 2, 3, 4 and 5. It means the number of possible heads obtained. Therefore, for each situation you have to obtain the probability value. The calculation was shown here. Using this calculation, we can obtain this value. Here, if I just brief about this 5c, here what we need to know is these concepts need to know by ourselves. Factorial 0 is equal to 1. 1 factorial is equal to 1. And n factorial can be written as n times n minus 1 times, likewise 3 times 2 times 1. These are the concepts we need to follow out. And ncx can be given written as n factorial times n minus x factorial divided by x factorial. If I write down the value for 5c0, then this can be written as 5 times 5 minus 0 times divided by 0 factor. Then this can be considered as 5 times, here 5 minus 0 is 5 divided by 0 factor. What we know is I will find out the 5 factorial value later. 0 factorial is 1. Therefore, we will get this as 5 factorial into 5 factorial. Therefore, we will get this the value of factorial 5. If I write it here, then this can be considered as 5 multiplied with 4 multiplied with 3 multiplied with 2 multiplied with 1. If you perform this multiplication, 5 into 4 into 3 into 2 into 1, You will get this as 100, and therefore here we will get the value as 120 into 120. Therefore this multiplication gives the value as 144 with 2 zeros. Therefore this is the value that we can get as 5C0, and it is the value that we can get at this point, but using a scientific calculator you can easily obtain this value. Here there is a mistake which I have done. I have written this equation which is not in the correct way. I have just changed the numerator and denominators. Therefore, this should be actually written as NCX is given as n factorial divided by r this x factorial times n minus x factorial. This is the correct equation. In the previous, if I have misinterpreted this, please consider this as the correct equation. This is the correct equation. And if I redo the calculation, this can be easily done. It is 5C0, then this can be considered as 5 factorial divided by x factorial is 0, then 5 minus 0 factorial. Therefore, this can be considered as 5 divided by 0 factorial. It is 5 minus 0. It is again 5 factorial. Therefore, these two cancel out. Then we know that 0 factorial is equal to 1. Here above value is 1 and denominator is 1. Then we'll get 5C0 is equal to 1. This value is equal to 1. Here it is no need to do these calculations this much lengthy. And anyhow, if I explain another example based on this this notation NCX, if I use this NCX notation, if I need to use it for calculation of 5C2, we'll see how we can obtain this value. If you see if it is 5C2, then we can say this as it is 5 factorial divided by 2 factorial, 5 minus 2 factorial. Then this can be written as 5 factorial divided by 2 factorial into 3 factorial. Then 5 factorial can be written as it is 5 times 5 multiplied by 4 multiplied by 4 multiplied by 3 times 2 times 1 can be written as 3 factorial. It is because here it is go up to 1, therefore no need to do much more calculation. It is because here we can see that 3 factorial is here, then 5 times 4 20 divided by 2 is equal to 10. Therefore here we can take this value equals to 10. But using this proper calculation, you can obtain these values. Therefore, here if you are considering, if I take this 0.00243, this is the probability that we are getting exactly 0 heads out of these 5 trials. Therefore, it is interpreted in that way. If I choose this value, it is 0.3787, 3087. The probability of getting exactly 3 heads out of the 5 trials is equal to 0.3087. Therefore, now we need to calculate all these 6 values. It is because in the first part, it asks us to find out the probability distribution. Therefore, the probability distribution has calculated in this way. Now you can see in the table, the calculated values are included. Here, these are the values which we have calculated at this point. And if you see about the summation of these six values, then this should be exactly equal to 1, or approximate to 1. This is the summation of these values are approximate to 1. And now it is the first part. In the second part, it is asking probability that exactly one head obtained. Now it is no need to just go for further calculations. It is because now you have already identified what is the probability value where we getting where x equals 1. Here we can say that where x equals 1, we are getting the probability as 0.02835. Therefore, this is what we are getting as the probability value. We are getting exactly 1 heads. And for the next part, probability that exactly 3 heads obtained. 3 heads obtained, we are getting x equals 3. The value is 0.3087. And if I show you the answers for these two, here I have directly obtained them since I have obtained it in this system. But for the part B and C, if you just wish to do the calculation again, exactly 1 head, then you have to follow this calculation for the part B. And if you need to redo the calculation for the part C, probability that exactly 3 heads obtained. Therefore, 3 heads obtained. Here we have to use this as the calculation of part C. And in the calculation of the next one, it is probability that at most 4 heads obtained. At most 4 heads means the maximum number of heads that we can obtain is 4. It means that the number of heads should be less than or equal to 4. It means that if you go through this probability that at most 4 heads obtained, prior to this, if I write down what we have identified so far, it is 5 and 0.7. Then at most 4 heads, here we have n equals 5, p equals 0.7. And here it says that at most 4 heads obtained means that we need to find out where the x is less than or equal to 4. It is because we have identified x equals to number of heads obtained. Therefore, here what we need to identify is probability of x less than or equal to 4. It means at most 4 heads obtained. Therefore, what we can do is the possible values that we can take where x less than or equal 4. What we know is possible values of x are 1, 2, 3, 4, and 5. These are the possible values. Therefore, what we can do is we can find out all the possible outcomes here. It is the summation. Since it is given as a cumulative density function, we need to identify this. Then x less than or equal 4 means the possible values that we can take for x is x equals 0. Then probability of x equals 1. Then probability of x equals 2 can be taken. And then probability of x equals 3 can be taken, as well as probability of x equals 4 can be taken here. Therefore, the summation of these 5 values gives the probability for this quantity. But again, no need to calculate the probabilities. It is because we are having the value for 0, 1, 2, 3, and 4. It means that summation of these 5 values gives us the probability of x is less than or equal 4. Therefore, this calculation gives us the value as 0.747178. This can be considered as the probability of at most 4 heads obtained is 0.4717. This is one method you can use to calculate for calculation of this type of question. And then You can use the next way also. The next way we can use here at most four heads. See, actually, this has to be corrected. At most four heads means this can include four as well. Therefore, this should x equals 4. Then the answer should be changed. And then this has to be added to where px equals 4 is 0.36015. So this should be 0.36015. Then if you go through this calculation, at most four heads, then we'll have to add this 0.471782. The quantity is 0.36015. Therefore, this value is equal to at most four head is 0.83193. Therefore, this should be the correct answer. And if I redo the calculation for this part, then we can get this as probability of x. Here it is less than or equal 4. This can be considered as 1 minus probability x greater than 4. Therefore, it is because we know that the total probability of any given situation should be equal to 1. Therefore, here we are considering the events which are getting values less than or equal 4. Then it should be equal to 1 minus probability x greater than 4. Then if you perform this calculation, then what we can take here is probability of x greater than 4. The possible values are probability that x equals 4. This is the only possible value we can have. Now we have to calculate this value, but in this calculation it is no need to do it by us. It is because we have already calculated this value as 0.16807. This value was calculated as 0.16807, and this also gives us the value as 0.83193. Now you can see that both way the answers are correct. Both answers are both ways gives us the same answer. And if you move for the next part, it asks us that calculation of the at least three heads obtained. At least three heads obtained. To take the at least three heads, what we can see here is at least three heads obtained means we need to identify probability of x is greater than or equal 3. In this situation, we can identify that the possible values are probability of x equals 3 should be there, then probability of x equals 4 should be there, and probability of x equals 5 should be there. Using this concept, we can easily take the values. Here we can see that this calculation leads us to a value that it is 83692. The addition of these three values gives the value as 0.83692. Or else you can use the other way around as well. If you need, you can say that probability of x greater than or equal 3. This suggests that this equals to 1 minus probability x less than 3. Then x less than 3 in the sense the possible values are probability of x equals 0, probability of x equals 1, and then the probability of x equals 2. These are the possible values we can take, and even though you followed this way, you must get the value as 0.83692 or value which is approximate to this value. This is how we are calculating, we are performing the calculations based on the binomial distribution, and two other parts have included here. Here it asks us to calculate the expected value and the variance of this experiment. We know that if it is a binomial distribution, we know that the expected value of the binomial distribution can be obtained using the equation n times p. Now what we know is value of n is equals to 5 and value is p is known as zero point 0.7. Then if you substitute the values 5 times 0.7, we are getting the expected value as 3.5. Means that averagely 3.5 hits would be there among these 5 tossers. Then variance of x can be obtained using the equation n times p times 1 minus p. If you do the substitution, it is 5.7 is here. 1 minus 0.7 is 5 times 0.7. 0.3 suggests that value is equal to 1.0. This is how we are calculating the expected and variance for the binomial distribution. And here I have included another example. You can first try this by yourselves, and then you can just see for the answers as well. And here you can see the answers as provided, and try to do this by yourselves, and please go through this example as well. And this is all what I need to discuss for this session. And thank you all for participating in this session.